You guys made it to your final exam review. That means you're almost done with the semester. I don't know if you can see my shadow, but I'm dancing over here for you guys. I'm so excited. All right, so we're going to talk about nomenclature or naming. As the first topic, we're going to go through and finish all these topics. I might have to stop and start a few times and edit this back together, but all right, let's just go ahead and get started without further ado. So we're going to start by talking about, again, naming ionic and covalent compounds. It tells you also to know naming of acids. Now, one important thing to know is acids are covalent compounds. They're two or more nonmetals, but when you place them in water, they become aqueous because they ionize. So what makes an acid is that it gives off H plus and it's aqueous. So because it gives off H plus, it's almost always going to start with an H. So this first situation here, we have something that starts with an H and it's aqueous. That means it is an acid. So we know right away that it's going to end in acid. The next thing we say is, what kind of acid is it? Well, this hydrogen is bound to something that has no oxygens. If it has no oxygens, we're going to write hydro. Hydro means no O in it. And then we just fill in whatever that thing is that it's bound to. This looks like a chlorine, so this becomes chloric. If you want very specific ones, I have a whole video on nomenclature if you need additional help. All right, moving on to this next one. Oh, in this case, we have something that starts with an H plus and it's aqueous, but the situation here is that there are oxygens. If there are oxygens, then we don't use the word hydro. So we just call this chloric acid. Now, why we call it chloric acid is ClO3 negative is chlorate. We change chlorate to chloric. If we had something like ClO2 negative, we would have, which would be chlorite, we would have changed that to chlorous acid. All right, just for fun, what if I have HClO4? Aqueous. If you remember, ClO4 would be perchlorate, so this would be perchloric acid. Charges matter when we're looking at acids. For example, chlorate, it has a 1 negative, and that's why we only added 1 H plus to give us this chloric acid. The next question is SO3. It's easy to look at SO3 and think, oh no, that's sulfite or some kind of polyatomic ion. But remember, the key word of ion is that it has a charge. This thing does not have a charge. This is neutral. Because it's neutral, this is simply sulfur trioxide. These are two or more nonmetals. And that's why we're going to follow the nonmetal naming structure. The only time you follow nonmetal naming structure is when you have, whenever you have nonmetals, that's when you follow the di, tri, tetra, etc. This next one, however, does have a charge. This is an ion. This is sulfite. If you don't know that that is sulfite, you are behind. Go memorize the polyatomic ions. There's a video on polyatomic ions here as well. Okay, magnesium, I almost gave it away right here. This is magnesium chloride. This is an ionic compound. In this case, we don't use di, tri, tetra, di, tri. All that stuff is gone because we have metal and nonmetal. When we have a metal and a nonmetal, they're ionic. And that's when they rely on their charges to figure out how many of each thing you need. So magnesium, for example, is in the second row in the periodic table. It would have a +2 charge. I'm going to save some room because I'm going to move helium over, I know that. And because it has a +2 charge, chloride over here has a -1. We don't even need to know that. We know that there's 2 chlorides, so they must each be -1. And this is magnesium chloride. Let's go backwards. Let's say we did not know what magnesium chloride was, and I said, hey, what is the formula of magnesium chloride? Again, we use the periodic table. We say, okay, well, we know magnesium is 2+. We know chloride is -1. We need 2 of them, and that is why MgCl2 must be your answer. All right, moving on to this next one. It's a syn. If you don't know tin, Sn is tin. Next, this is an ionic compound. We got a metal and a non-metal. Although we talked about it in the last lecture, you should definitely at this point understand where metals and non-metals are. Down here and to the left, we're talking about metals. Up here and to the upper right, we're talking about non-metals. Tin is a metal. So tin bound with this thing, which we should recognize as carbonate, is essentially saying, hey, you got a tin and you have 2 carbonates. Well, we know that each carbonate is CO3 2 negative. If you got 2 of them, what must the charge of tin be? It has to be positive 4 or 4 plus. And so in naming this thing, if we go over and look at tin, the charges for each column, for example, this is 1 plus, 2 plus, 3 plus, 4 plus or minus, 3 minus, 2 minus, 1 minus, and 0. If we go and look at tin, these charges don't apply for things under the stair stepper. So we got this tin 4, so that's why this tin 4 plus works. Even though it works out this way, tin has varying charges and you can't count on the periodic table. So this would be tin 4 carbonate. We use Roman numerals when charge isn't known from the periodic table. So we can look at the periodic table. We don't know the charge of tin. Yes, it happens to fall under 4 plus. It's a horrible example, but I'll come across a few more that won't be as bad of examples throughout this, this lecture. So again, any transition metal and anything under the periodic table is when you'll use Roman numerals. This is when you'll use Roman numerals. All right, moving on through. Calculations involving density. Yeah. I just realized I forgot my calculator, so I gotta run upstairs and grab it. But you won't even know because I'll splice these together. Watch the pen, it won't even move. Boom, I'm back. Okay, so it says calculations involving density. It says of a regular and irregular shaped object. So the example I've given in class is that I find some kind of weird object in my yard, or my kids do, and we're like, hey, I wonder what the density of that object is, because that's the first thing you wonder when you find a weird object. And so density, it says to know the equation. I hate equations. Density has units almost always of grams per milliliter, which is also equivalent to grams per centimeter cubed. Milliliter is equal to centimeter cubed. That's because a centimeter cubed of water has a volume of 1 milliliter. So centimeter cubed also equals a milliliter. It's good to know, and you need to know it. Okay, so we take this irregular object and we're like, hey, what's its density? In other words, how many grams is in its volume? And first, we can take and put it on a scale, and it says, hey, it's got a mass of 9.0 grams. Well, now we need to divide that by its volume, either in milliliters or centimeter cubed. An irregularly shaped object, you can't just measure it and get a centimeter by centimeter by centimeter or something to that effect. Instead, what we have to do is put it in water. So let's say we put it in water. It starts out at 10.0 milliliters. When we place it in water, the water level goes up by, in other words, it's been displaced by 4.5 milliliters. So it goes up to like 14.5 milliliters. This is a difference of 4.5 milliliters. I just want you to have an idea of where this 4.5 milliliters would have come from. So if I ask you what the density of it is, make sure you're paying attention to the units that are given to you on the exam. So there'll be like multiple choice answers, and it'll tell you which units to use that inherently has the equation in it. Because if the units given to you are in grams per milliliter, then you're like, hey, I need to take the number of grams and divide it by milliliters. This gives me an answer of 2.0 grams per milliliter. Okay, now in this case, it says, hey, you've got this regularly shaped object. It's got a side length of 2.5 centimeters. It's a cube, so kind of like here, it's going to be 2.5 by 2.5 by 2.5. So we're going to take 2.5 times 2.5 times 2.5. Centimeters times centimeters times centimeters would give us centimeters cubed. So 2.5 cubed. Gives me an answer of 15.63 centimeters cubed. Its mass is 64 grams, and it asks what its density is. Well, we just take 64 grams divided by 15.63 centimeters cubed. And I get an answer of 4.096, or we could round that to 4.1 grams per centimeter cubed with appropriate sig figs. All right, next it says, know the abbreviations of different physical states for each reactant and product in a chemical, for states used for reactants and products in a chemical reaction. Okay, so this is when we're talking about solids, liquids, and gases, but these aren't just some kind of random thing that we throw at the end. I want you to actually think about this in terms of a chemical reaction. All right, this is baking soda and vinegar reacting. This is vinegar. We know that vinegar is an acid, right? It starts with an H. What physical state does an acid have to be? Aqueous. So this would be aqueous. I did not leave nearly enough room. And this aqueous acid, meaning it's dissolved, aqueous means dissolved, is reacting with NaHCO3. This is sodium bicarbonate. You could throw in even solid sodium bicarbonate. It would have to dissolve in order for it to react, but if you think about baking soda, it's actually a solid. In fact, you know what? I'm gonna pause this and go make this reaction happen in front of you so we can talk about the states better. Okay, let's get to it. So I have a tray right here. And here, let's go ahead and go in order. Here I've got my aqueous vinegar. In other words, this is actually about 5% acetic acid and the rest is water. Here we have sodium bicarbonate, which is a solid. And essentially when I mix this in here, this is actually going to start dissolving and then reacting with the vinegar. So it bubbles. Oh, that's the best reaction ever. I don't know why people don't do that for everything. It teaches so much. Okay, so hopefully that was a blast. Almost literally. And we knew that this was a solid. In the reaction, it actually became aqueous as it began to react. So the solid state that you saw, that was a solid, right? It has a fixed shape, but and also a fixed volume. And then when we reacted them together, we got sodium acetate, which is dissolved. If you look in there, or you could actually taste this water now, it wouldn't be as vinegary, and instead it would taste more salty. And CO2 is a gas. In fact, there's so much CO2 in here, you'd be unable to light a flame. So if I took a flame and put it in there, it would put the flame out. And water. Water is its own physical state. It's not dissolved in itself, is what I'm trying to say, and it is a liquid. So physical states actually matter. It's not just some kind of crazy random thing that we're throwing out there. They help describe what happens in a reaction. We took aqueous acetic acid, we took solid sodium bicarbonate, which ended up dissolving in the water, became aqueous, and we formed sodium acetate, which is aqueous dissolved, carbon dioxide, which gave us the bubbling. That's how you know there's going to be bubbling in a reaction, and water liquid. Okay. Next, I ask you to know the components of the atom. Atoms are made up of protons, neutrons, and electrons. The protons are in the center. I guess it looks to me like I'm drawing beryllium here. So beryllium, let's go ahead and look at it. Beryllium has 4 protons. We would write the 4 right there if we're drawing a specific notation that gives you a number of protons. But this is redundant. Beryllium must have 4. In fact, here's how you know. Hydrogen has 1, helium has 2, lithium has 3, 4, 5, 6, 7, 8, 9, 10, etc. The number that is on the periodic table is the number of the protons that thing has. The number, let me get a better pen. On the periodic table is the number of protons it has. This cannot change. Cannot. I can spell cannot. It can't change, like, at all. There's nothing you can do to make the number of protons it has change. If it's got 4, it's beryllium. If it's beryllium, it's got 4. These things are attached. Now, the number of neutrons can change, number of electrons can change, but not the number of protons. Okay, then we have electrons. For neutral beryllium, we would have 4 electrons. And that's because we have 4 positives, so we must have 4 negatives to cancel it out. Neutrons come in down here because positive and positive repel each other, right? Neutrons come in and they act like a glue. They hold everything together. They keep those positive things from pushing each other apart, like 2 of the same ends of a magnet would push each other apart. The neutrons come in and help hold them together. So as the neutrons are holding them together, this number can vary. It can be 4, it can be 5, it can be 3, kind of depends on the situation. Let's say that there are 1, 2, 3, 4. Let's go ahead and make a 5th to make a point. There are 5 neutrons in this thing. If there are 5 neutrons in this thing, its mass number up here will be 9. This is the number of protons plus neutrons, whereas this is just the number of protons. If you want to quickly find the number of neutrons in something and you don't have a beautiful picture like this, then you just take the mass number minus the number of protons, and that gives you 5. That's the number of neutrons. Okay, it says to be able to interpret isotopes, including atomic and mass number. So let's talk about how isotopes play into anything, and even let's see what isotopes actually are. So sodium, for example, no, let's do neon. Neon's an easy example. So we've got neon. Neon has 10 protons. Why? Because it's neon, it's number 10 on the periodic table. Like, you have to put that in your head, and it's one of the most commonly missed things, despite the fact that I say it a lot. Okay, now it has varying isotopes. It's got a neon 21. It's got a neon 22. And I don't think this one's stable, but let's just throw it in there. It's got a neon 23. Okay, and yeah, just for the sake of teaching a lesson, I'm going to throw in a neon 20. Okay, so it actually really has 3 main isotopes. This one I made up, but let's just pretend it's there. Okay, so we got neon 20, neon 21, neon 22, and neon 23. In other words, we have one neon that has, they all have 10 protons, but one neon that has 10 neutrons, because I took 20 minus 10 gives us the number of neutrons. One that has 11 neutrons. One that has 12 neutrons. And this last one over here has 13 neutrons. Now let's say this was a multiple choice question, A, B, C, D. And the question is, which is the most abundant? So the mass of neon, if you look at the periodic table, is 20.2-ish. So the actual mass is 20.2. This mass is none of these masses, right? This mass is almost 20, this is about 21, this is about 22, and this one's about 23. So there is no one atom of neon. There are isotopes of neon. So if you grabbed a sample of neon and you held it, there would be some that have a mass of 20, some that have a mass of 21, 22, 23, etc. But the question is, which is the most abundant? In other words, if you picked up a sample, which one of these isotopes would you most likely grab, or would there be the most of in a sample? Because the mass is closest to 20, this one would be the one that's the most abundant, and A would be your answer. Again, mass is about 20, so A is your answer. All right. I would We just have so much to cover, y'all. Otherwise, I'd go into more detail, but I hope at this point you've got an idea of it already. Okay, and if you don't, there's a video for that. Okay, understanding hydrogen electronic transitions and the Bohr model of the hydrogen atom. Okay, so anytime we get to wavelength, frequency, energy, any of these issues, we're going to talk about our one master equation. If you remember, it is the change in energy of an atom is equal to the energy of a photon, is equal to h nu, where h is Planck's constant, nu is frequency, which is equal to hc over lambda. That's because frequency equals c over lambda, is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared. Now, there's a lot of people asking about, well, what about Rydberg equation and things like this? Well, Rydberg equation is derived from this equation, so this equation actually encompasses everything. Rydberg can save you an extra step, but it is one extra thing to remember, and it flips these things, and it gets kind of annoying in my opinion, and I think negative 18 and negative 18 is really easy to remember, so that's why I almost always do this equation. Not almost always, I always use this equation. Okay, so this is using the Bohr model to determine the energy in joules of a photon when an electron in a He+. How come we can use He+? This says hydrogen, because He+ has just, helium is here, it has 2 protons. Neutral helium would have 2 electrons, but if we take one of those electrons away, it only has 1 electron. So He2+, lithium, or He1+, lithium 2+, beryllium 3+, etc., have only 1 electron. In all of those situations, when you have just 1 electron, you can use a Bohr model. Okay, so we're looking for the number of energy of a photon and an electron when, so if this is 1, 2, 3, 4, and 5. So we've got something going from the 5 to the 2. Moves from orbit with n equals 5 to the orbit with n equals 2. So it goes down from here down to here. First of all, which type of light would this be? To give you an idea already of what kind of wavelength they're looking at. Well, if you remember, if we have something falling to n equals 1, that's UV. If we have something falling to n equals 2, that's visible. If we have something falling from it to n equals 3, 3 to 5, that's IR. So here we have an electron, it's falling, it's going down to n equals 2, it's going to produce some kind of visible light. What do we know about visible light? We know its wavelength, we know its generally where it's going to end up falling, and so we're talking about like 400 to 800 nanometers. UV vis is higher energy, it's falling farther, and when something falls farther, it produces a higher energy or a louder sound, and so here we're going to look at things that are going to be less than, actually probably closer to less than 350, but less than, yeah, let's just put less than 300. This is a gray area. And then IR as well is going to be greater than about 800 nanometers. So knowing those few things will actually help you in a multiple choice exam, because what if this question had been about wavelength? You'd be able to look at this and in 1 second be like, oh, it falls to n equals 2, that's going to be this many nanometers, and know it like that. Okay, now let's actually answer the question. It says, what is the energy? So we're looking for the energy of a photon, so we pull that part out of the equation, and it gives us the ends, so we pull that part out of the equation. These are the 2 parts of the equation that we're going to work with. I'm going to write down here because this is all the same stuff anyways. So our energy of the photon equals negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared equals negative 2.18 times 10 to the negative 18 joules times 1 over n final. Our final was 2, so 1 over 2 squared minus 1 over our initial was 5. So this is 1 over 4 and 1 over 25 equals go ahead and do it. Times. And I get an answer of -4.578 times 10 to the negative 19 joules. In other words, this atom, when that thing fell, lost this much energy in a photon. So the energy of the actual photon would be the absolute value of that. So we're looking at 4.58 times 10 to the negative 19 joules. Does this make sense? Oh yeah, it does. In fact, almost always is going to be around 10 to the negative 19, but a way that you can look at this is the maximum amount it can be is 2.18 times 10 to the negative 18. That's the maximum amount of energy a single photon is going to have when we're looking at these problems. So that would be your answer. Boom shakalaka. Now let's say, just for fun, let's say I asked you for the wavelength of this transition. Well, we know that this was how much energy it has, and we know that that's equal to hc over lambda, because energy of photon equals hc over lambda, where lambda is the wavelength. Now we can just solve for the wavelength. We know that h is 6.626 times 10 to the negative 34 joules times seconds. We know that c is 3.00 times 10 to the 8 meters per second. And we're going to divide that by wavelength. In other words, I'm going to take wavelength, I'm going to multiply it over there, and then I'm going to divide by the joules. So I've got I like to use all the numbers all the way through, 4.578 times 10 to the negative 19. Again, I'm setting that equal to 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by the wavelength. And I get an answer that wavelength is 4.34 times 10 to the negative 7 meters. I know it's meters because this was in meters. But I also know that there are 10 to the negative 9 meters in a nanometer. And this would give me an answer of 434 nanometers. Hey, we knew that. We knew it had to be in here. And so that is the answer that we end up getting from that transition. All right, so hopefully all this makes sense. You could do this and then figure out frequency. I'm not going over it. You spent a whole chapter on it, and I think as long as you got a reminder of the equations, you'll be better off. All right, number 8 says, know what the different quantum numbers mean and shapes of the orbitals. Okay. So I left this rather open for myself to lecture. I did give you the d orbital shapes because I can't do them justice in drawing them anyways. These are just the different shapes of the d orbitals. When we're talking about quantum numbers, actually let's go ahead and just do something crazy here. Let's look at sulfur. Sulfur's number 16 on the periodic table. Hey, it's got 16 protons. Just for funsies, its most stable isotope is probably right around 32. Has a mass number right around 32. So sulfur, if we want to know its electron configuration, we want to set our periodic table up for success. So right at the beginning of when you get an exam, I think it's really beneficial for you to take and go through and put all the charges up here. I think it's beneficial for you to remember these, these semi-metals. This one's kind of, people argue about it, but gives you an idea. To remember the semi-metals, it's also beneficial for you to label the S, move helium over here, P, D, F. To remember that S is 1, 2, 3, 4, 5, 6, 7. We started with 1 with S, so P will start 2, 3, 4, 5, 6. We started with 2 with P, 3, 4, 5, 6. 3 with D, so 4 and 5. It's also good to remember the exceptions. Underline them, outline them. I will tell you, I told you guys to do this on the last exam. It was like the number one missed question was the exception to the rule because you guys didn't do this. So print out a periodic table, underline these exceptions so you remember that they're exceptions when you get there. All right, and now you've set yourself up for success on electron configuration and any kind of questions about electron orbitals or quantum numbers, etc. Okay, so we said we're doing sulfur. Sulfur has an electron configuration starting at neon. I'll do it on a separate piece of paper. Sulfur has an electron configuration starting at neon. And it looks to me like after neon it's 3s2, 3p4. So 3s2, 3p4. Now let's say I want to know, again it has 16 electrons, I want to know the quantum numbers. Of things in outer shell, of electrons in outer shell. In other words, the valence electrons. Okay, so we want to know the quantum numbers of electrons in the outer shell, in other words, the valence electrons. So the valence electrons here, they're going to be these 6 electrons. We've got 2 in the 3s and 4 in the 3p. If we were drawing this out, we'd say this is the 3s and this is the 3p. 3p has 3 orbitals in it. It's got a px, a py, and a pz, and we don't even know which one goes in which thing. We just kind of arbitrarily name them px, py, and pz. Okay, so as we add electrons, this one has 2. Remember, you go 1 up and 1 down. And this one has 4. 1, spread them apart. Electrons hate each other. They don't want to be paired up until they have to be. 1, 2, 3. And then when they are paired up, they take opposite spins so that they don't have, so they don't clash. Let me put that one in there. Okay, so make sure you're spreading them apart. Make sure you have an idea of how to do this. This was electron 1, then 2, 3, 4, 5, and 6. And it's necessary to do this in order to understand quantum numbers. Okay, the question said, essentially, what are the quantum numbers of all these? Well, this, when I go through and do something like this, I like to take and label the middle one. That's 0. And this one, there's 1, 2, 3. I put the middle one there, 0. To the right, I add +1. To the left, I add -1. These are my m sub l's. These represent the orbital, the type of orbital that those things are in. Now, yes, they're all p orbitals, but this will tell me if it's a px, a py, or a pz. So, so let's say I ask you for the quantum numbers. I asked you for the quantum numbers of everything in there, but let's specifically do one, and then we can do all of them together. So the quantum numbers of, let's say the 4th, no, let's do the 6th. T. The 6th electron here, which would actually be the 16th of sulfur. So let's look at the 6th electron in this situation that we planted. Quantum numbers, there are 4 of them: N, L, M sub L, and M sub S. N tells you which number it's in. So when we're talking about electrons in the previous problem falling from n equals 5 to n equals 2, it's the exact same n. So here it's saying we have n's in each case of 3, but we're looking at the 6th one here. This one is has an N of 3 because it's 3p. Now we look at the L. L you just have to memorize. It's just a way of, instead of saying S, P, D, or F, instead of saying which orbital it's in, it just gives you a number because they're called quantum numbers. So this is 0, 1, 2, and 3, and you can go on and on if you want to. But L in this situation, because it's a P, is going to be 1. Okay, this was a P, so we went over here, we're like, oh, the L to represent P is 1. The M sub L is going to be, again, these, which we labeled. We start with the middle one right here, and we go add 1 and subtract 1, and that gives us the M sub L. So in this situation, we're talking about an M sub L here of -1. And its M sub S is simply, is it spinning up or is it spinning down? It's going to be plus or minus 1/2. So the M sub S, plus or minus 1/2. You just have to determine if it's up or down. Because we were very careful when we labeled this, this one is down, and that's -1/2. And those would be the quantum numbers of that particular electron. So it's important that we understand where these come from rather than just memorizing a set of stuff, which is what I've seen a lot in books and in other lectures, that people don't actually take the time to figure out what exactly is happening. So this tells us a lot about the electron. If we drew sulfur, it's saying, hey, you got 2 electrons in this s orbital, and then you got these p orbitals. You got a px, a py, and a pz. And it's saying, hey, in your px, you have 2 electrons. And your py, you have 1. And your pz, you also have 1. And it's saying, hey, one of them spinning one way, so one of these lobes is spinning one way, and one of these lobes is spinning another way. So you can even tell exactly where that electron, the perimeter in which that electron is located using quantum numbers. And that is the point of quantum numbers. It tells you, hey, there's an actual electron in a particular orbital that looks like this, just given this set of information. Okay, so allowed quantum numbers for sulfur. In other words, which quantum numbers are there? Well, we have an N in all of these situations was an N of 3. We have an L of 0 and 1. We have an M sub L of -1. We have zeros, and we have +1. And we have an M sub S of plus and minus 1/2. So all these are allowed quantum numbers for this particular thing. Sorry, I know this is all over the place. I shouldn't end every question with, I hope you understood it. But if you did not understand it, then go back to when we originally talked about quantum numbers in chapter 8, I believe. All right, moving on. All right, so in this question, it says no different quantum numbers mean and know the shapes of the orbitals. S is like this. P is a dumbbell shape. There's 3 p orbitals and a p subshell. So when we're talking about this is a subshell, and we have 3 orbitals within it. Here we have D. There are 5, because if you remember, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each orbital fits 2 electrons. So this is a D subshell, has 5 different orbitals. So just understand those shapes. Usually they'll just say, which of the following is the shape of a p orbital? And then one of the answers will be dumbbell. And that would be your answer. Number 9, writing electron configuration of elements and ions. Don't forget the exceptions. Okay, so like I said, make sure you underline those in the periodic table. Hey, we've done this. What is the electron configuration for sulfur? We just did it. I'm going to skip over it. What is the electron configuration for mercury? Mercury loves hugs. Okay, it's right here. The nearest noble gas is xenon. So let me go ahead and pull this up here. The nearest noble gas is xenon right here. And so we're going to start with xenon. After xenon, we go through here. We've got a 6s2. And then we've got a 5 5d10. But wait a second. When we get to 5s and 6s, that's when we take a little break. We go through the F's, and then we come back. In other words, this whole set of blocks fits right into here, these lanthanides and actinides. So to reiterate, we've got 6s2, then we hit this spot right here. Then we've got to go through the 4f14, then we go all the way back to the 5d, and we happen to be 5d10. All right, if I took away 2 electrons, where you want to take them from is the highest number first. The highest number was not a 4 or 5, the highest number is 6. Anything in the transition metals will always take away from the highest number. Well, they'll always take away from the highest number, but the highest number will always be these S's over here, and this is why we do the S's first. So these are higher energy. We want to remove the higher energy electrons to make a more stable structure. So when we pull off Hg2+, we're taking away those 2, and that's why Hg2+ would be xenon 4f14 5d10. Some people will write 6s0. That one is going to be up to you. Okay, which neutral atom has an electron configuration of 4s2, 3d10, 4p3? Let's go ahead and look. It said 4s2, 3d10, and then it was 4p3. 4s2, 3d10, 4p, 1, 2, 3. Arsenic. Whoops. Can't believe that. I was just thinking of some kind of way you guys could remember arsenic, and I wrote the wrong thing. Okay. I can't do it without cursing. I came up with something, but that would be inappropriate. So let's move on to this one. 4s2, 3d9. So we go to 4s2, 3d9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait a second. We highlighted that one. Isn't that one an exception? It is. Why is that an exception? Oh yeah, because copper is not 4s2, 3d9. Copper wants to fill its d subshell, or its d subshell, so that it's completely lower in energy. So copper's electron configuration is actually argon 4s1, 3d10, because it takes one of the electrons from the 4s and becomes this. Just for funsies, in case you're worried about how ions go, copper plus would still take from the highest number right here. It would be 3d10. What about copper 2 plus? That's when we can now take away from the leftover highest number, which would be this one. So, oops, 3d9, excuse me. So this question of 4s2, 3d9 does not exist. I can see a question trying to trick you, and you're getting into things, and that's why it's so important that you highlight these, okay? Writing orbital diagrams of elements and ions. We actually did this already when we're talking about like 4s, 3d, and we fill these in. These are orbital diagrams. Just understand that you got to spread out the number of electrons, etc. Sometimes you'll see them horizontal, sometimes you'll see them linear. It just depends on the situation. All right, number 11, periodic trends. So I think this kind of does it already. Isoelectronic species. I see the question that's gonna get at. So let's go ahead and do that. So general trends are like this. Atomic size, this is for a neutral. So I see why we have isoelectronic species. We'll go ahead and go through that real quick. Ionization energy is almost always up and to the right, though there are those exceptions. If you remember, those exceptions were in group 3, I'm trying to do some stuff in my head, group 3 and group 6. And so that's because I didn't do a good job, that's 3, and group 6. Sorry, 3 and 6. The reason for that is it takes very little energy for something to lose an electron and then become a full shell. I don't want to go through it. I was just thinking, should I go through it? I don't want to go through it. I've already gone through it in a lot of detail in other lectures, so go back to those other lectures. This particular one, trying to remember, it has to be, I believe it's in chapter 8 lectures, where I actually ask a specific question and we go through each individual exception and try to figure out what's going on and why it happens the way it happens. Okay, so neutral atoms, chapter 8 lectures for exceptions. Electron affinity, remember fluorine is most electronegative, meaning it has the highest affinity for electrons. Now let's go through these isoelectronic species, so questions that I really think might show up, because I think ultimately that's what's going to help you more than just going through stuff that won't. Let's go ahead and look at isoelectronic species. So let's say we have argon. What's isoelectronic to argon would be chlorine with 1 extra electron, because that would make its electron configuration the same as chlorine. So let's say we have, or same as argon. So argon, Cl minus, S, 2 minus, would have the same electron configuration as this. So these are all what we call isoelectronic. Potassium over here can lose an electron and be just like argon, and so can calcium. Now, if these were neutral species, and I asked you for what's smaller, sulfur, chlorine, argon, potassium, or calcium, you should automatically go up and to the right and look at argon. However, these are not neutral. These have charges to them. In fact, each of them has 18 electrons. So they all have 18 electrons on the outside, but what do they differ in? Hopefully you're thinking the number of protons, because again, the numbers are changing as we go over here. Sulfur, for example, always has to have 16 no matter how many electrons it has. So argon here has 18. Chlorine here has 17. Sulfur has 16. Potassium has 19. And calcium has 20 protons. And I say, which is smaller? Well, what determines the size of a species is essentially how much its protons are pulling those electrons to the center. Because if you think about it, all that makes up an atom is protons and electrons. So if you pull those electrons closer, you're going to have a smaller atom. So which is smallest? Well, we look for the one that has the most protons in the center. This one has the most protons in the center, meaning it's got a stronger pull. This is like having 20 magnets. Over here, we only got 16. If you got 20 magnets, you're going to pull those electrons a little bit harder. They're going to be coming in a little bit closer, and that's what makes this one the smallest. By the opposite reasoning, this one has less of a pull. Sulfur has the fewest protons in the center, and this would be the biggest. It doesn't have as much of a pull. Okay, now we're looking at relationships between mass and grams per mole. If you guys remember, the song goes like this: to turn grams into moles, divide by molar mass, grams into moles, divide by molar mass, grams into moles, divide by molar mass, and if you don't, you're a pain in my... All right, so we're gonna go ahead and put grams into moles by dividing by molar mass. Now, to lay it out in a little more literally, we turn grams into moles by dividing by molar mass. And we should do this every time we see a question that has any kind of grams. You immediately turn it into moles. But there are often times a question will ask you more information, like how many atoms, how many molecules, etc. And in those situations, then you got to turn mole into molecules and molecules into atoms. Now to turn moles into molecules, that's when we use 6.022 times 10 to the 23rd molecules per mole. And then molecule to atom is specific to the atom. It depends on the atom, or it depends on the molecule. So let's go ahead and practice this. It says calculations involving mass, moles, and entities. How many carbon atoms are in 47.2 grams of hexane? So from the beginning, you should know how to do this. But let's go ahead and do the whole way through, including even remembering what hexane is. Hex tells you that there's 6 carbons. Ane tells you that they're singly bound. Now and the reason I'm doing this is because I would immediately take this and divide by molar mass, right? We've got grams and I want to divide by the molar mass, but I can't because I don't know the molar mass. So I'm not going to Google it because I'm taking an exam, so instead I want to actually figure it out. Each carbon must have 4 bonds, so we put a hydrogen, 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 hydrogen. Wow, that's really annoying to say. I won't say it anymore. Okay, and now if we go and count them up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And if you remember, another quick way to do it is when we have an ane, is to multiply the carbons by 2 and add 2. 6 times 2 is 12, plus 2 is 14, and that would be hexane. So it says we got 47.2 grams of hexane. We know we want to turn grams into moles, and it wants to know how many atoms there are. So it wants us to get all the way to atoms. So we have to go to grams to moles, so we need the molar mass. Then we can go moles to molecules and molecules to atom. To get the molar mass, we say, hey, we've got 6 times 12.01 grams per mole of carbon, plus 14 times 1.008 grams per mole hydrogen. Now, pretty much in this exam, I really expect you to be given the molar masses, but at the same time, it never hurts to know how to do it as backup, or remember how to do it as backup. Okay, in this situation, I get an answer of 86.17 grams per mole. And now we can start this question. It says, start with 47.2 grams. To put grams into moles, divide by molar mass. The molar mass is 86.17. Now we're in mole town. Now it really helps to be thinking about what you're talking about. This was the molar mass of hexane. Now down here, we've got to go from mole to molecule. Well, we know a mole of anything has 6.022 times 10 to the 23rd of those things. And we're still talking about hexane. Now we're in molecule town. We know that a molecule of C6H14 has, this depends on the molecule, and this is what I mean, it has 6 carbon atoms, 1, 2, 3, 4, 5, 6. So I'm going to take 47.2 times 6.022 times 6 divided by 86.17. Now, you can, anything that's on the bottom, you just put a division sign in front of it and it'll work out. 47.2 times 6.022 times 10 to the 23rd times 6 divided by 86.17. And I get an answer of, how many sig figs? Looks like there's 3. I get an answer of 1.98 times 10 to the 24 carbon atoms. All right. Now it says, what mass of a sample of lead 4 sulfate? What is the mass of a sample of sample of lead 4 sulfate containing this many oxygen atoms? Now it gives you the number of atoms, and it asks you essentially to find the mass. I should have put in grams, so let's go ahead and put in grams. So now we're going from atoms to molecule, molecule to mole, and mole to gram, so kind of go in the opposite direction. Without further ado, let's go ahead and do it. We've got 4.31 times 10 to the 24 oxygen atoms. It gives us the molar mass, but if this is atoms, what has to go here? Oh yeah, atoms. And we're going straight from atoms to molecule. In this case, this is an ionic compound. It's also called formula unit. Some people still call it molecule. It just depends on who's writing it. So in order to figure this out, we also have to know what lead 4 sulfate is. That's cool because we remember that lead 4 is Pb4 plus. We know that sulfate is SO4 2 minus. How many sulfates do we need? 2 to cancel that charge out. So lead 4 sulfate is Pb SO4 2. It looks to me like one of these has 8 oxygen atoms. Again, each sulfate has 4, and you've got 2 sulfates. So there are 8 atoms and 1 molecule of this lead 4 sulfate. Now we're in molecule town. Now we can get to moles. We know if this is molecule, what has to go here? Molecule. We're going from molecule to mole. And we know that there's 6.022 times 10 to the 23rd molecules in a mole. Now we're in mole town. We're getting closer. We got to get all the way to gram town. We know if that's mole, this has to be mole. And we know that there are 399.32 grams in a mole. Now we're set. We can figure this out. I'm going to take 4.31 times 10 to the 24 times 399.32 divided by 8 divided by, in parentheses, 6.022 times 10 to the 23rd. And I get an answer of 357, almost a whole mole's worth of lead 4 sulfate. Okay, next question. What is the mass percent of carbon in caffeine? And it gives you the formula of caffeine, and it gives you even the molar mass. It's not usually provided in questions like this because they expect you to know how to add up the mass of everything and figure it all out yourself. Essentially, we've got a molecule of caffeine. It has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. Remember, each of these things have different masses. Hydrogen's really light. Oxygen's the heaviest thing in here, the more massive thing in here. And so the mass percent it's looking for has nothing to do with, let me rephrase that. The mass percent that they're looking for has pretty much to do with how much weight one particular amount of an atom gives to the entire molecule. So we've talked about it in terms of somebody holding a football, or and we say, what's the mass percent of that football? There's various things that what's the mass percent of water in you? It's pretty high. You consist of a lot of water. Okay. So essentially, mass percent equals what you're interested in divided by the total mass times 100%. Let's make this simple. There are 8 carbons, so we have 8 times 12.01 grams per mole, because that's their mass, divided by the total mass, 194.19 grams per mole, times 100%. So I'm going to take 8 times 12.01 divided by 194.19, and then times 100%, I get an answer of 49.48%. So because there were 8 carbons, it takes up almost half of the mass of the entire molecule. Cool. Let's get crazy. Okay, it says what is the empirical formula? If you remember, empirical formula is kind of like the most reduced formula. It tells you relative ratios of things. So for example, hydrogen peroxide is H2O2. Let me redo this. This is its molecular structure telling you, or molecular formula telling you there are 2 hydrogens and 2 oxygens in 1 molecule of hydrogen peroxide. However, its empirical formula, so let me write that, that was molecular. Its empirical formula, you would divide each of these by 2 because it's a common denominator, and we get HO. That's the empirical formula, telling you for every 1 hydrogen, there is 1 oxygen. So this is a molecular formula. It tells you there are 2 hydrogens and 2 oxygens in a single molecule. The empirical tells you relative ratios. For every 1 hydrogen, there is 1 oxygen. So this is asking for the empirical formula given this information. Well, we're given percents. When you're given percent like this, and a question asking for empirical molecular formula, you pretend that you've got a 100-gram sample. If you've got 100 grams and 49.5% of it is carbon, and that means that you've got 49.5 grams of carbon. So first we're going to start by turning everything into grams. Hey, what do we do once we have grams? Turn grams into moles by dividing by molar mass. So 49.5 grams divided by 12.01 grams per mole. And we're going to do this for each of these. I chose a really long problem. Why, I don't know. Oh, I remember why. Divided by 12.01. And this gives me an answer of 4.12 mole. Here I take 5.19. I'm going to divide it by 1.008 grams per mole. And I get an answer of 5.14 mole. Here I've got 28.9. I'm going to divide it by 14.01 grams per mole. And I get an answer of 2.06. And then I do the same with oxygen, 16.5. I'm going to divide it by 16.00 grams per mole. And I get an answer of 1.03. Okay? We already know the relative ratios now of this particular compound. The particular compound right now is C, 4.12, H, 5.14, N, 2.06, O, 1.03, but that looks a little cray-cray. So what we're gonna have to do is find a way to reduce this so that we actually have whole numbers. To do that, you find the smallest one. So what's smaller of all these numbers? Hopefully you're saying 1.03 is the smallest, and it is. What you do is you go through and you divide each of these numbers by 1.03. So at least this one now gives you a 1. That one gives me a 1. 2.06 divided by 1.03 will give me 2. Even though I can do this next one in my head, I want to see exactly what it comes out to so I can write it down for you guys so you know when to come into this situation. Here I get 4.99. That's pretty darn close to 5. We're rounding up to whole numbers unless you get a half, like a 0.5 or a 0.33 or something that's obvious. You're going to round to the nearest whole number. You're going to have to use some of your instincts here. And then we have 4.12 divided by 1.03, which would give me 4, telling me that the actual empirical formula is C4H5, N2O, C4H5N2O. This is the empirical formula. I said, hey, if the above compound has a molar mass of 194.19, what is its molecular formula? Keep in mind, this is its empirical formula. This is not hydrogen peroxide. This is the empirical formula of hydrogen peroxide. We have to have the molar mass of this one in order to figure out the actual molecular formula. What I mean by that is this. We have an empirical formula here, C4H5N2O. We want to know its molecular formula. We are given information that its molecular formula is 194.19 grams per mole. But we have to calculate something over here to figure out exactly what the molecular formula ends up being. That's its molar mass, because then we can figure out how many times bigger its molecular mass is from its actual empirical formula mass. So to do that, we're going to say 4 times 12.01 plus 5 times 1.008 plus 2 times 14.01 plus 1 times 16.00. Let's go ahead and do that. Oops. So we got 48.04. And I get an answer of 95.08 grams per mole. Okay, so let me do that again. 48.04 plus, yeah, I am missing. There we go. 5 times 1.008 plus 28.02 plus 16. Yeah, 97. That makes more sense. My bad. I get 97.1 grams per mole. Okay, so when I add all these up, I get about 97. The good thing is these are usually just going to be about, so this would actually say something like between 190 and 200 or something crazy like that. So now we say, okay, we know the empirical formula is 97.1. The molecular formula is how many times bigger? It looks to be about 2 times bigger, or you could take 194.19 divided by 97.1 and find out that's about 2. Telling you the molecular formula has 2 times the mass. We can't change these ratios. For every 4 carbons, there have to be 5 hydrogens to 2 nitrogens and 1 oxygen. It has to be that same ratio. That's the empirical formula of the thing. Keeping that same ratio, then, we have to double the mass. In order to double the mass, we have to double every single thing in here, and that will give us a molecular formula. So we're talking about twice the amount of carbons, twice the amount of hydrogens, twice the amount of nitrogens, and twice the amount of oxygens. And this would be the molecular formula. If you add up the mass of this, it's about 194. It's the only thing that makes sense keeping this same ratio. So that would be the molecular formula. If you look back to the previous question, we actually started with what is mass percent of caffeine? I gave you caffeine molecular formula, and we found out the mass percent is 49.5% carbon. How cool! Mass percent here was 49.5% carbon. So we kind of went all the way in using mass percent and then all the way back to the original compound, whether you knew it or not. All right. Whew. We're getting there. Stoichiometry and limiting reactant calculations. It says you react 85 milliliters of a 1.2 mole per liter solution. We have liters and mole per liter. What we like to do with liters and mole per liter is multiply them together. Make sure that this is put into liters, 0.085 liters. And we say times 1.2 mole per liter. Before I even read the question, I like to do that, just like with changing grams into moles. So 0.085 times 1.2 gives me an answer of 0.102 mole. How I knew that was mole is because we took liters and we multiplied it by mole per liter. Liters canceled and we were left with mole. With 148 grams of calcium bromide, 148 grams of calcium bromide. Who did not give you the molar mass of calcium bromide? That would be me. I'm annoying. Okay, grr. Let's go ahead and add it up. Calcium has a mass of 40.08. So we're going to take 40.08 plus 2 times the bromide, which is 79.9. I know. And that will give us the molar mass of calcium bromide, which will allow us to turn grams into moles, which is what we have to do. So 40.08 plus 2 times 79.9 gives me a mass of 199.88 grams per mole. So I'm going to take that 148 and divide it by 199.88, because to turn grams into moles, you divide by the molar mass. This gives me an answer of 0.7404. Okay, so that's in mole. And it says 16 grams of precipitate was covered. Wait, what the heck is precipitate? Precipitate is a solid when you have a double displacement reaction. Here we took silver, nitrate, and calcium bromide. We got silver bromide and calcium nitrate. The ions switched. And so this one is insoluble. That's how we knew it was a solid. You have to know your solubility rules to figure that out. So we figured out that this one was a solid, and that's the precipitate that it's talking about. So let's go ahead and figure out how many moles this is too while we're at it, because anything that's in here I like to know. Silver has a mass of 107.87 grams per mole. Whoops, mole. Plus bromide was 79.90. 107.87 plus 79.9 gives me an answer of 187.77. Grams per mole. In other words, we'll take that 16 divided by 187.77, and that will tell us how many moles of precipitate was recovered. And I get an answer of 0.0852 mole. Let's go ahead and do this. So the question is, what is the percent yield of the reaction? I'm going to rewrite this reaction so we got plenty of space to work with, and figure everything out. 2AgNO3. Again, this was an aqueous solution. You were given liters and mole per liter. Plus CaBr2. This is aqueous, but it told you the solid amount, which is fine. Yields 2 silver bromide plus calcium nitrate. I like to put the starting amounts here. What we started with 0.102 mole of silver nitrate. We started with 0.7404 mole of this calcium bromide. It says that this much was recovered. In other words, we actually made this much precipitate. This would be like our actual yield. Our actual yield, I like to write on the reaction. I like to put like our initial stuff or our change or our actual. Here we can put change. In other words, we made 0.0852 mole of this. Now we could figure out how much calcium nitrate we made, because stoichiometry tells us for every 2 silver bromides we had to have made 1 of these. In other words, half the amount. So I could put 0.04-ish over here. But that's not really the question. The question is, what is the percent yield? Percent yield equals actual over theoretical times 100%. We already know our actual. It's almost always given to us in the problem. If it's not, then it will be asking for the actual yield, and we just follow the opposite procedure. Divided by our theoretical yield. Our theoretical yield is how much in theory we should have made. Well, to figure that out, we have to look at the reaction of what we started with. Here we had 0.1 silver, here we had 0.7 of the calcium bromide. So it looks to me like this is a limiting reactant. Don't forget though to divide by the coefficients, especially if they're really close or you can't tell looking at it. I would divide this by 2, I divide this by 1, and I ask which one's smaller. This is my limiting reactant. So down here, our theoretical yield is going to be equal to our 0.102 mole of our silver nitrate. And we know for every 2 mole of silver nitrate, what are we interested in finding? Well, our actual yield was this, so our theoretical yield also needs to be in mole of silver bromide. So for every 2 mole of silver nitrate, you got 2 mole of silver bromide. So it happens to be a 1-to-1 ratio. We'll get an answer of 0.102 mole of silver nitrate. So our theoretical is 0.102 mole of silver nitrate times 100%. So our actual we found from the problem. Boy, I cannot spell this morning. Problem. This one, the theoretical, we had to solve using the limiting reactant amount, and then we multiply by 100%. So let's go ahead and do it. We've got 0.0852 divided by 0.102. And I get an answer of 83, and then multiply by 100%, 83.5%, or about 84% if you look at sig figs. Cool. So in other words, of what you expected to make, you actually made 84% of it. That covered a lot. That covered solution stoichiometry, so make sure you remember that big M is mole per liter. That covered turning grams into moles. That covered precipitation reactions. That covered double displacement reactions. This one question covered a lot, so make sure you really understood it. Balancing reactions, I'm not going to go into. You can use deductive reasoning to figure out if a multiple choice test has a correct balanced reaction, or you just need to know. I also have videos, short videos even, of balancing equations and balancing reactions, so make sure you check those out if you need extra help. Calculations involving percent yield, we just did it. Calculations involving molarity, we just did it. I'm going to call it a day on those. If you need help with dilutions, I'm going to post some additional lectures for you guys for solution calculations, so that you have a better idea. Understanding how salts disappear in solution, or dissolve salts appear in solution. I don't really know what that means. Or maybe it's talking about double displacement reactions. So I'm going to cover 2 things. I feel like there's a typo there. So I'm going to cover 2 things. One, we talked about sodium chloride dissolving in water. The reason it dissolves in water is because hydrogen and oxygen and water each have different charges. Oxygen now we know is bent shaped, right? Water is bent shaped, and those electrons like to hang out around the oxygen, and that's why this gets a partial negative charge. It's also more electronegative, so these are going to be polar bonds. In other words, a dipole is going this way, telling you the overall electron pull is going up to the oxygens, and that's why it has a partial negative. That leaves this guy with a partial positive. And so when you put sodium, which is at Na plus, and Cl minus, they have a choice. They can stay together and remain a solid, or they can break apart. In this case, they're going to break apart. We get Cl negative here, we get Na plus here, and they're broken apart, and that's how you get an aqueous solution. Now, let's go ahead and say you have something like sodium chloride, and we react it with lead-2 nitrate. In a double displacement reaction, sodium chloride and lead-2 nitrate will form sodium nitrate, which would be aqueous, and lead-2 chloride, which would actually be a solid according to your solubility rules. So what happens here is you've got this dissolved container that has Na plus and Cl minus in it. You have a dissolved container which has I really can't spell, Pb2 plus and nitrates in it. And when you mix these two, what happens is lead is like, what's up, chloride, and it grabs a hold of it. And you have a few chlorides in here. So it grabs 2 of these and it forms a solid, and they come out of solution. So maybe that's what it's talking about how they would appear, is this is how you end up getting a precipitate or like a cloudy solution. In any labs that you guys have done, you've seen cloudy coming out of 2 clear solutions. When you mix them together, you get something cloudy. That's a precipitate being formed. Number 21, solution stoichiometry. Just go ahead and look at At the above one, we have milliliters of a mole per liter kind of thing. Number 22, write the net ionic reactions, precipitation, and acid-base reactions, and identifying spectator ions. I don't know what that means, but I'm just going to do what I feel like doing. So if we were to break this down, again, kind of like we did up here, in solution, this is saying, hey, you've got a beaker maybe, or some kind of container with 2 silvers in it, 2 silver ions, 2 nitrate ions. How did I know 2? Because this was saying you got 2 silver nitrates. So you got 2 silvers and 2 nitrates. They're aqueous, telling you they're broken apart. I'm going to look at everything that's aqueous and I'm going to break it apart. Over here we have another thing that's aqueous. That's 1 calcium. It's got a 2+ charge, and 2 bromides. Then they come together. And what happens is when you mix this solution and this solution, the silver and the bromides are like, hey, what's up? And they form this silver bromide. So you get 2 AgBr solid, and you know that they form because it makes a solid. So this is the precipitate. Plus, hey, over here we still got calcium, which is aqueous, and we got 2 nitrates. So everything that was aqueous, I broke apart and I kept it as an ion, and then over here we have something solid. So what this is saying is you got these 2 clear solutions, you mix them together, you got a solid, and you got calcium and nitrate hanging out. Hey, guess what else you had over here? You still had calcium and nitrate hanging out. They didn't do anything. Calcium and nitrate are on this side, calcium and nitrate are on this side, they did nothing. So overall, we don't really want them in an equation. And that's why when we talk about our net ionic equation, we're saying, hey, take those things out of here. Those things happen to be called spectator ions. They did nothing in the reaction. However, I'm going to show you a shortcut. Instead of breaking this down and possibly making a mistake, let's say we didn't know all this, and we're just given this equation, and we're saying, what's the net ionic equation, and what are the spectator ions? What we do is we look for the state that's not aqueous. Hey, that's aqueous. Hey, that's aqueous. Hey, that's not aqueous. You underline it. Hey, that's aqueous. You write it down. 2 AgBr solid. So you write it down, and then you say, hey, what did it take to make silver bromide? And in fact, I'm going to have you write it down without the coefficients. Let's just save yourself time and write it down without the coefficients. So we had silver bromide. What did it take to make silver bromide? Hey, it took silver and it took bromide, and that's what it took to make silver bromide, and that would be your net ionic equation. Spectator ions would be whatever's left over here that's on the aqueous side. We had calcium and we had nitrate. In other words, there were calcium ions and nitrate ions just hanging out in that solution. Now, what is the net ionic equation when sodium hydroxide, NaOH, you should know that, reacts with sulfuric acid? Sulfuric is not hydrosulfuric, it's sulfuric, telling you that there's going to be oxygens. We're talking about that. So let's go ahead and react these together. NaOH plus H2SO4. Now, if you remember, when we're reacting acid bases, an H plus and an OH minus form together to make water. Again, one H plus and one OH minus form together to make water. In this case, we only have one OH minus here, but here we've got 2 H pluses. So we want to balance this reaction starting at the beginning to make it easier on ourselves. Here we have 1 water. We want to make 2 waters, so we need 2 OH minuses because we want to use up all these H pluses. So now we put a 2 there. And this is going to react to form 2 waters. And then whatever's left. Again, we've used up the OH minus, we've used up the H plus. All that we have left is 2 sodiums and 1 sulfate. What a convenient thing that is, because sodium sulfate is Na2SO4. If you remember, sodium is aqueous. What about water? Oh, it's a liquid. Let's talk about the net ionic equation now. The net ionic equation, we look for the thing that's not aqueous. Aqueous, aqueous, not aqueous, aqueous. We write it down. We ask what we use to make water. What did you use to make water? You use an OH minus and you use an H plus, and this will always be the case for strong acid, strong base reactions. And that would be the net ionic equation. What about the spectator ions? Oh yeah, the spectator ions are the things that are aqueous over here. In other words, sodium and sulfate. Woohoo! Good job. Now on to our last thing. I essentially just said know strong acids and know the strong acids and strong bases. There's a video that says where I talk about memorizing strong acids and strong bases. I referred to a lot of videos in here, so I'm sure that's kind of annoying, but I want you guys to be able to pick and choose what you need. I don't know, let's make that quotes. Again, yeah, there will be more videos, shapes, or more questions in the actual final exam. Shapes are not covered on this, as you can see, but that doesn't mean they're not going to show up. In fact, I really expect them to show up. I expect there to be questions very similar to your previous exams, in fact, as well. So these will tell you exactly, you know that these kind of questions are going to be on there. Add extra stuff to fill in any gaps that might show up as well. All right, y'all. I hope this helped. I hope it gave you some idea of what to do. And I hope you watch the other videos if you need additional clarification and for much more detailed step-by-step instructions. I will miss you all. I did 80 push-ups today. I really, really want to get 100 by final exam time, so it's coming, y'all. Give me a few more days. All right, I love you guys. Have a good one. Bye.